Alright, welcome back. Today we're going to be learning about imaginary numbers in Algebra 2 on khanacademy.org. So we have a couple videos to watch and a couple articles to read, and so that's what we're going to be doing today.
In this video, I want to introduce you to the number I, which is sometimes
Uh, Sal talks a little bit slow, so I'm going to speed it up to 1.5 for the
called the
videos.
imaginary unit. And we're going to see here, and it might be a little bit difficult to fully appreciate right from the get-go, it's a more bizarre number than some of the other wacky numbers we learn in mathematics like pi or e. And it's more bizarre because it doesn't have a tangible value in the sense that we're normally used to defining numbers. I is defined as the number whose square is equal to -1. This is the definition. This is the definition of I. And it leads to all sorts of interesting things. Now, some places you will see I defined this way. I as being equal to the principal square root of -1. I wanted to just point out to you that this is not wrong, and it might make sense to you. You know, if something squared is -1, then maybe it's the principal square root of -1. And so these seem to be almost the same statement. But I just want to make you a little careful when you do this. Some people will even go as far as saying this is wrong, and it actually turns out that they are wrong to say that this is wrong. But when you do this, you have to be a little bit careful about what it means to take a principal square root of a negative number and it being defined for imaginary, and as we'll learn in the future, complex numbers. But for your understanding right now, you don't have to differentiate them. You don't have to split hairs between any of these definitions. Now, with this definition, let's just think about what the different powers of I are. Because you can imagine, if something squared is -1, if I take it to all sorts of powers, maybe that should give us all sorts of weird things. And what we'll see is that the powers of I are kind of neat because they kind of cycle, or they do cycle, through a set of values. So I could let's start with I to the 0th power. And so you might say, hey, look, anything to the 0th power is 1, so I to the 0th power is 1, and that is true. And you could actually derive that even from this definition. But this is pretty straightforward. Anything to the 0th power, including I, is 1. Then you say, okay, what is I to the 1st power? Well, anything to the 1st power is just that number times itself once. So that's just going to be I, really by the definition of what it means to take an exponent. So that completely makes sense. And then you have I to the 2nd power. I to the 2nd power, well, by definition, I to the 2nd power is equal to -1. Let's try I to the 3rd power. I'll do this in a color I haven't used. I to the 3rd power. I to the 3rd power. Well, that's going to be I to the 2nd power times I. And we know that I to the 2nd power is -1, so it's -1 times I. Let me make it clear. This is the same thing as this, which is the same thing as that. I squared is -1. So when you multiply it out, -1 times I, we'll write as -I. Now what happens if we take I to the 4th power? I'll do it up here. I to the 4th power. Well, once again, this is going to be I times I to the 3rd power. So that's I times I to the 3rd power. I times I to the 3rd power. But what was I to the 3rd power? I to the 3rd power was -I. This over here is -I. And so I times I would give you -1, but you have a negative out here. So it's I times I is -1, and then you have a negative. That gives you +1. That gives you positive. Let me write it down. So this is the same thing as, so this is I times -I, which is the same thing as -1 times, remember, multiplication is commutative. If we're just multiplying a bunch of numbers, we can switch the order. This is the same thing as -1 times I times I. I times I, by definition, is -1. -1 times -1 is equal to 1. So I to the 4th is the same thing as I to the 0th power. Now let's try I to the 5th power. I to the 5th power. Well, that's just going to be I to the 4th times I. And we know what I to the 4th is. It is 1. So it's 1 times I, or it is just I again. And so once again, it is exactly the same thing as I to the 1st power. Let's try, and just to see the pattern keep going, let's try I to the 7th power. Or sorry, I to the 6th power. I to the 6th power. Well, that's I times I to the 5th power. That's I times I to the 5th. I to the 5th, we already established, is just I. So it's I times I. It is equal to, by definition, I times I is -1. And then let's finish off. We could keep going on this way. We can keep putting higher and higher powers of I here, and we'll see that it keeps cycling back. In the next video, I'll teach you how taking an arbitrarily high power of I, how you can figure out what that's going to be. But let's just verify this cycle keeps going. I to the 7th power is equal to I times I to the 6th power. I to the 6th power is -1. I times -1 is -I. And if you take I to the 8th, once again it'll be 1. I to the 9th will be I again, so on and so forth.
Alright, now we're going to do the article. Um, Alright, so intro to imaginary numbers. I don't know why I went to the bottom there. In your study of mathematics, you have noticed that some quadratic equations do not have any real number solutions. For example, try as you may, you you will never be able to find a real number solution for the equation x squared equals -1. That's because it's impossible to square a real number and get a negative. However, a solution for the equation x squared equals -1 does exist in a new number system called the complex number system. So the imaginary unit, the backbone of this new system, the imaginary unit, or the number I, the following. So the backbone of this new number system is the imaginary unit, or the number I. The following is true of the number I equals the square root of -1, and I squared equals -1. So these are just like, you know, inverses pretty much. The second property shows us that the number I is indeed a solution of the equation x squared equals -1. The previously unsolved equation is now solvable with the addition of the imaginary unit. The number I is by no means alone. By taking multiple of this imaginary unit, we create infinitely more pure imaginary numbers. For example, 3i, I square root of 5, -12i are all examples of pure imaginary numbers, or numbers in the form of b of I, where b is a non-zero real number. Taking the squares of these numbers sheds some light on how they relate to real numbers. Let's investigate this squaring by the number 3i. By squaring the number 3i, the properties of integer exponents remain the same, so we can square 3i just as we'd imagine. So we take 3i, square it, square everything inside the parentheses. So that's 3 squared and I squared, so that's 9i squared. Using the fact that I squared equals -1, we can simplify this further as shown. So we take I squared equals -1, sorry, and that's -9 when you multiply it out. The fact that 3i squared equals -9 means that 3i squared has a square root of -9. Check your understanding. What is 4i squared? So what we're going to do here is we take 4i here, and I'll just do it here, 4i, but we take 4 squared, which is 16, and then we take I squared, which we know I squared is -1. So we take -1 times 16, so that'd be -16. So we'll check our answer here, and we got it right. So which of the following is a square root of -16? Well, as we see here, -16, if we square it, it'd be 4i, because 4i squared equals -16, so this would be 4i. There we go. In this way, we can see that pure imaginary numbers are the square roots of negative numbers, simplifying pure imaginary numbers. The table below shows examples of pure imaginary numbers in both unsimplified and simplified form. Unsimplified, simplified. Alright, but just how do we simplify these pure imaginary numbers? Let's take a closer look at the first example and see if we can think through the simplification. Original equivalence would be -9, the square root of -9 equals 3i. So the square root of -9 is an imaginary number. The square root of 9 is 3, so the square root of -9 is 3 imaginary units, or 3i. The following properties explain the above thought process in mathematical terms. So a is greater than 0, so square root of -a equals I square root of a. So if this number in the parentheses is greater than 0, well, I guess here it would be less than 0. If -a is less than 0, then it then the square root of that number is the square root of that number imaginary units. The square root of that number and then imaginary units right after that. Alright, so here's an example. Simplify square root of -18. Well, if we take the, well, we know here that 18 is greater than 0, so that works. So that we take the imaginary units times the square root of -18. Now, square root of -18 doesn't really, I think, it doesn't come out clean, so we'll just go square, so it'd be I square root 18, and that's sort of what they did here. Yep, so I square root 18. Oh, I guess you could do I square root 9 times 2, And then they did, yep. Oh, and then they took 3, so 3I square root 2. So simplify square root, so we're going to do some practice problems now. Simplify the square root of negative 25. Well, we know that I up here, that A, which would be this number in here, 25 is greater than 0. So we take, I'm actually going to pull up a little thing right here. So 25 is greater than 0. So the square root of negative 25 equals I times the square root of 25. And we know this because the original formula is if A is greater than 0, then negative A, square root of negative A equals I times square root of A. So we're taking the positive A, and we're taking I times the square root, so that'd be I, so it'd be 5I actually, because of the way you order it. So it'd be 5I, we'll check, and we got it right. Now simplify square root of negative 10. Well, 10 is greater than 0, so, oh shoot. Nope. Well, 10 is greater than 0, so if we take 10, so the square root of negative 10 equals I times square root of 10. And then we can, let's see, what can we simplify that to? I think that's as far as that can be simplified, so I times square root of 10. Yep. Now we take the square root of negative 24. Well, 24 is greater than 0, so the square root of negative 24 equals I times the square root of 24. And let me think. So 4 and 6 can go into this. It'd be I times 4 times 6. So that'd be 2I square root of 6. 2I square root 6. There we go. Why do we have imaginary numbers? Anyways, the answer is simple. The imaginary unit, I, allows us to find solutions to many equations that do not have real number solutions. This may seem weird, but is actually very common for equations to be unsolvable in one number system, but solvable in another. Okay, I gotta read that again because I kind of confused myself. This may seem weird, but it's actually very common for equations to be unsolvable in one number system, but solvable in another. Okay, more general number systems. More general number, what? This may seem weird, but is actually very common for equations to be unsolvable in one number system, but solvable in another, more general number system. Should there be a comma there? I think, I don't know. Yeah, there should be a comma there, right? I don't know. Here are some examples with which you might be more familiar. With only the counting numbers, we can't solve x plus 8 equals 1. We need integers for this. With only integers, we can't solve 3x minus 1 equals 0. We need rational numbers for this. With only rational numbers, you can't solve x squared equals 2. Enter irrational numbers in the real number system. And so with only real numbers, we can't solve x squared equals negative 1. We need imaginary numbers for this. As you continue to study mathematics, you will begin to see the importance of these numbers. Alright, now simplifying roots of negative numbers.
We're asked to simplify the principal square root of negative 52. And we're going to assume, because we have a negative 52 here inside of the radical, that this is the principal branch of the complex square root function, that we can actually input negative numbers in the domain of this function, that we can actually get imaginary or complex results. So we can rewrite negative 52 as negative 1 times 52. So this can be rewritten as the principal square root of negative 1 times negative 1 times 52. And then, if we assume that this is the principal branch of the complex square root function, we can rewrite this. This is going to be equal to the square root of negative 1 times the the principal square root of negative 1 times the principal square root of 52. Now, I want to be very, very clear here. You can do what we just did. If we have the principal square root of the product of two things, we can rewrite that as the principal square root of each, and then we take the product. But you can only do this, or I should say, you can only do this if either both of these numbers are positive or only one of them is negative. You cannot do this if both of these were negative. For example, you could not do this. You could not say the square root of, or the principal square root of 52 is equal to negative 1 times negative 52. You could do this so far. I haven't said anything wrong. 52 is definitely negative 1 times negative 52. But then, since these are both negative, you cannot then say that this is equal to the square root of negative 1 times the square root of negative 52. In fact, I invite you to continue on this train of reasoning. You're going to get a nonsensical answer. This is not okay. This is not okay. You cannot do this right over here. And the reason why you cannot do this is that this property does not work when both of these numbers are negative. Now, with that said, we can do it if only one of them are negative or both of them are positive, obviously. Now, the principal square root of negative 1, if we're talking about the principal branch of the complex square root function, is I. So this right over here does simplify to I. And then let's think if we can simplify the square root of 52 any. And to do that, we can think about its prime factorization, see if we have any perfect squares sitting in there. So 52 is 2 times 26, and 26 is 2 times 13. So we have 2 times 2 there, or 4 there, which is a perfect square. So we can rewrite this as equal to, well, we have our I now. The principal square root of negative 1 is I. The other square root of negative 1 is negative I. But the principal square root of negative 1 is I. And then we're going to multiply that times the square root of 4 times 13. And this is equal to, going to be equal to I times the square root of 4, or the principal square root of 4 times the principal square root of 13. The principal square root of 4 is 2. So this all simplifies, and we can switch the order over here. This is equal to 2 times the square root of 13, 2 times the principal square root of 13, I should say, times I. And I just switched around the order. It makes it a little bit easier to read if I put the I after the numbers over here. But I'm just multiplying I times 2 times the square root of 13. That's the same thing as multiplying 2 times the principal square root of 13 times I. And I think this is about as simplified as we can get here.
Alright, now we have another article to do. The power of the imaginary unit. So I'll drop me to the bottom again. We know that I equals the square root of negative 1, and that I squared equals negative 1. But what about I to the third or I to the fourth? Other integer powers of I. How can we evaluate these? Finding I to the third and I to the fourth. The properties of exponents can help us here. In fact, when calculating powers of I, we can apply the properties of exponents that we know to be true in real number systems, so long as exponents are integers. I'm going to read that again because I didn't really understand that. Alright, so the properties of exponents can help us here. So the properties of these exponents, right there. In fact, when calculating powers of I, we can apply the properties of exponents that we know to be true in the real number system, as long as the exponents are integers. Okay, so we can multiply and divide them and add them normally, as long as they're all integers. So we know that I to the third equals I squared times I, but I squared equals negative 1. We see that we can negative this I squared, make it a negative 1 times I, so it'd be negative I. Similarly, I to the fourth equals I squared times I squared. So if we use I squared equals negative 1, we have 1. So keep going. I to the fifth equals I to the fourth times I, so that'd be 1 times I, so that'd be I. And then I to the sixth is I to the fourth times I to the second, that'd be negative 1. I to the seventh is negative I to the eighth is 1. So it goes I, negative 1, negative I, 1, I, negative I, 1, I, and so on and so forth. So it goes the 1, and then the negative, and then the I, and then the negative 1, negative I. So from the table, it appears that the power of I cycle through the sequence of I, negative 1, negative I, and 1. Using this pattern, we can find I to the 20th. So following the list shows the first 20 numbers in repeating sequence. According to this logic, I to the 20th should be equal to 1. Let's see if we can support this with exponents. Remember that we can use properties of exponents just like we did with real numbers. So we could do I to the 4th, to the 5th power. So that's going to be 1. I to the 5th, well, that's just 1. So we do see that I to the 20th is 1. So let's suppose we wanted to find out I to the 138th. Well, we could list I, negative 1, negative I, 1 out to the 138th, but that would take too long. So now, but I to the 4th is 1, I to the 8th is 1, I to the 12th is 1. So for every time we raise I by a multiple of 4 is 1. So for every I that's a multiple of 4 is 1. So we can use this fact along with the properties of exponents. So I to the so 138 is not an exponent, is not a multiple of 4, but 136 is. So if we go to 136, that starts with I. So 137 would be, okay, so we could just do this here. 136 times I to the 2nd, well, that would be I to the 4th times I to the 34th times I to the 2nd. So that would be 1 to the 34th times negative 1. And then, so negative 1 is our answer. You could also go I to the 36th, and then I to the 37th would be negative 1, and I to the 38th would be negative I. So there you go. Also, you could use that. So I to the 38th would be negative 1. Now you might ask why we choose to write I to the 38th as I to the 36 times 2. Well, if the original exponent is not a multiple of 4, then finding the closest multiple of 4 allows us to simplify the power down to I squared, or I to the 3rd, just by using the fact that I to the 4th equals 1. This number is easy to find, and you divide the original exponent by 4. It's just the quotient without the remainder times 4. So now we're going to try some practice problems. Simplify 227, I to the 227th. So we're going to use our cheating calculator here. So we have 227. There we go. 227 divided by 4 equals 56.75. Well, what's 4 times 56? Because we just get rid of the remainder, and that's 224. So the way we would write this would be if we, oh shoot. If we clear this, don't save. If we clear this, we have I to the 227th equals, and we could simplify this down to I to the 224th. Sorry about my handwriting. It's not very good. I to the 24th times I to the, how much more is it to get to 27? It's 3. So now we can take this, and it'd be I to the 4th times I to the 200 to the 56th. 56th times I to the 3rd. Well, I to the 4th is 1. So I to the 156th. So we have 1 times I to the 156th, right? No, we don't need this I here. We can just multiply it in the exponents only. So now we have 1 to the 156th. Well, that's just 1 times I to the third times I to the third. And we know that I to the first equals I. I to the I squared is negative 1, and I to the third is negative I. So this is 1 negative I. So we kind of want negative I. Nope, that's not a T. 1. So negative I times 1 should be our answer. Negative I, 1. And there we go, we got it right. Now we need to simplify I to the 216th. I to the 216th. So we'll take, just clear, 216, that's not 216, 16 divided by 4. Well, it comes out to 504 even. So 216 is divisible by 4, so we know that since this is divisible by 4, I just equals 1. So we'll check. Yep. Now 537. So clear. 537 divided by 4 equals 134. Well, what's 134 times 4? That's 536. So since 536, I to the 536th is 1, and then we also have I to the first. Right? Let me work this out one sec. So I to the 537th equals I to the 536th times I to the first. Yeah, okay, so this will work. So I to the 536, well, we know that 536 is divisible by 4. So that simplifies down to 1 times I to the first. Well, I to the first is just I. So we have 1 I as our answer. Here we go. 1 I. Check. And we got it right. So now's our challenge problem. Which of the following is equivalent to I to the negative first? So if we follow our pattern, here, our pattern starts at 1. It goes I, and then negative 1, and then negative I, and then 1. So this would be I to the first, this would be I to the second, this would be I to the third, this would be I to the fourth. Well, if we go to 0, down here, 0 down here, well, we just take this one and put it back at the beginning since it's a pattern. Also, we know that anything to the power of 0 is 1. And then the next one, negative 1, next one in the order, would be negative I. So that'd be negative I. So our answer should be negative I. And we got it right. So now we're going to watch a video. 2 more
Now that we've
videos.
seen that as we take
Oh, where's that video playing? There we go. 2 more videos,
Now
and I
that
think
we've
we're going to be
seen
done
that,
for
that
today.
as we take I to higher and higher powers, it cycles between 1, I, -1, negative I, then back to 1, I, -1, and negative I want to see if we can tackle some, I guess you could call them trickier problems, and you might see these surface, and they're also kind of fun to do, to realize that you can use this, the fact that the powers of I cycle through these values, you can use this to really, on the back of an envelope, take arbitrarily high powers of I. So let's try, just for fun, let's see what I to the 100th power is. And the realization here is that 100 is a multiple of 4. So you could say that this is the same thing as I to the 4 times 25th power. And this is the same thing, just from our exponent properties, is I to the 4th power raised to the 25th power. Right? If you have something raised to an exponent and then that is raised to an exponent, that's the same thing as multiplying the two exponents. And we know that I to the 4th, that's pretty straightforward. I to the 4th is just 1. I to the 4th is 1, so this is 1. So this is equal to 1 to the 25th power, which is just equal to 1. So once again, we use this kind of cycling ability of I when you take its powers to figure out a very high exponent of I. Now let's say we try something a little bit stranger. Let's try I to the 501st power. Now in this situation, 501, it's not a multiple of 4, so you can't just do that simply. But what you could do is you could write this as a product of two numbers, one that is a multiple, one that is I to a multiple of 4th power, and then one it isn't. And so you could rewrite this. 500 is a multiple of 4. So you could write this as I to the 500th power, I to the 500th power, times I to the first power, right? You have the same base. When you multiply, you can add exponents. So this would be I to the 501st power. And we know that this is the same thing as I to the 500th power is the same thing as I to the 4th power. 4 times what? 4 times 125 is 500. So that's this part right over here. I to the 500th is the same thing as I to the 4th to the 125th power, and then that times I to the first power times I to the first. Well, I to the fourth is 1. 1 to the 125th power is just going to be 1. This whole thing is 1. And so we are just left with I to the first. So this is going to be equal to I. So it seems like a really daunting problem, something that you would have to sit and do all day. But you can use this cycling to realize, look, I to the 500th is just going to be 1. And so I to the 500th 1 is just going to be I times that. So I to any multiple of 4. Let me write this generally. So if you have I to any multiple of 4, so this right over here is, well, we'll just restrict k to be non-negative right now. K is greater than or equal to 0. So if we have I to any multiple of 4 right over here, we are going to get 1, because this is the same thing as I to the 4th power to the kth power, and that is the same thing as 1 to the kth power, which is clearly equal to 1. And if we have anything else, if we have I to the 4k plus 1 power, I to the 4k plus 2 power, we can then just do this technique right over here. So let's try that with a few more problems just to make it clear that you can do really, really arbitrarily crazy things. So let's take I to the 7,321st power. Now, we just have to figure out, this is going to be some multiple of 4 plus something else. So to do that, well, you could just look at it by sight, that 7,320 is divisible by 4. You can verify that by hand, and then you have that 1 left over. And so this is going to be I to the 7,320 times I to the first power. This is a multiple of 4. This right here is a multiple of 4, and I know that because any 100 is a multiple, any 1,000 is a multiple of 4, any 100 is a multiple of 4, and then 20 is a multiple of 4. And so this right over here will simplify to 1. Sorry, that's not I to the ith power. This is I to the first power. 7,321 is 7,320 plus 1. And so this part right over here is going to simplify to 1, and we're just going to be left with I to the first power, or just I. Let's do another one. I to the 90, I to the 90, let me try something interesting. I to the 99th, I to the 99th power. So once again, what's the highest multiple of 4 that is less than 99? It is 96. It is 96. So this is the same thing as I to the 96th power times I to the third power, right? If you multiply these, same base, add the exponent, you would get I to the 99th power. I to the 96th power, since this is a multiple of 4, this is I to the 4th, and then that to the 16th power, so that's just 1 to the 16th, so this is just 1, and then you're just left with I to the third power. And you could either remember that I to the third power is equal to, you could just remember this equal to negative I, or if you forget that, you could just say, look, this is the same thing as I squared times I. This is equal to I squared times I. I squared, by definition, is equal to negative 1. So you have negative 1 times I is equal to negative I. Let me do one more just for the fun of it. Let's take I to the 38th power. Well, once again, this is equal to I to the 36th times I squared. I'm doing I to the 36th power since that's the largest multiple 4 that goes into 38. What's left over is this 2. This simplifies to 1, and I'm just left with I squared, which is equal to negative 1.
Alright, now we have this last video, and then we're done for today.
In your mathematical careers, you might encounter people who say it is wrong to say that I is equal to the principal square root of negative 1. And if you ask them, why is this wrong, they'll show up with this kind of line of logic that actually seems pretty reasonable. They will tell you that, okay, well, let's just start with -1. We know from definition that -1 is equal to I times I. Everything seems pretty straightforward right now. And then they'll say, well, look, if you take this, if you assume this part right here, then we can replace each of these i's with the square root of -1. And they'd be right. So then this would be the same thing as the square root of -1 times the square root of -1. And then they would tell you that, hey, look, just from straight up properties of the principal square root function, they'll tell you that the square root of a times b is the same thing as the principal square root of a times the principal square root of b. And so if you have the principal square root of a times the principal square root of b, that's the same thing as the square root of a times b. So based on this property of the radical of the principal root, they'll say that this over here is the same thing as the square root of -1 times -1 of -1 times -1. If I have the principal root of the product of two things, that's the same thing as the product of each of their principal roots. I'm doing this in the other order here. Here I had the principal root of the products. Over here I have this on the right. And then from that, we all know that -1 times -1 is 1. So this should be equal to the principal square root of 1. And then the principal square root of 1, remember, this radical means principal square root, positive square root. That is just going to be +1. And they'll say this is wrong. Clearly, -1 and +1 are not the same thing, and they'll argue, therefore, you can't make this substitution that we did in this step. And what you should then point out is that this was not the incorrect step. That it is true, -1 is not equal to 1, but the faulty line of reasoning here was in using this property, when both a and b are negative. If both a and b are negative, this will never be true. So a and b cannot cannot be cannot be negative. In fact, normally when this property is given, sometimes it's given a little bit in the footnotes, or you might not even notice it because it's not relevant when you're learning it the first time, but they'll usually give a little bit of a constraint there. They'll usually say for a and b greater than or equal to 0. So that's where they list this property. This is true for a and b greater than or equal to 0. And in particular, it's false if both a and b are if they are both negative. Now, I've said that I've just spent the last 3 minutes saying that people who tell you that this is wrong are wrong. But with that said, I will say that you have to be a little bit careful about it. You have to be a little bit careful about it. When we take traditional principal square roots, so when you take this principal square root of 4, we know that this is +2. That 4 actually has two square roots. There's -2 is also a square root of 4. If you have -2 times -2, it's also equal to 4. This radical symbol here means principal square root. Or when we're just dealing with real numbers, non-imaginary, non-complex numbers, you can really view it as the positive square root. This has two square roots, positive and -2. If you have this radical symbol right here, principal square roots, it means the positive square root of 2. So when you start thinking about taking square roots of negative numbers, or even in the future we'll do imaginary numbers and complex numbers and all the rest, you have to expand the definition of what this radical means. So when you are taking the square root really of any negative number, you're really saying that this is no longer the traditional principal square root function. You're now talking that this is the principal complex square root function, or this is now defined for complex inputs, or the domain, and can also generate imaginary or complex outputs, or I guess you could call that the range. And if you assume that, then really straight from this, you get that the square root of -x is going to be equal to I times the square root of x. And this is only, and I'm going to make this clear because I just told you that this will be false if both a and b are negative. So this is only true. So we can apply this. We can apply this. We can apply when x is greater than or equal to 0. So if x is greater than or equal to 0, then -x is clearly a negative number, or I guess it could also be 0. It's a negative number, and then we can apply this right over here. If x was less than 0, then we would be doing all of this nonsense up here, and then we would start to get nonsensical answers. And if you look at it this way, and you say, hey, look, I can be the square root of -1 if we're taking if it's the principal branch of the complex square root function, then you could rewrite this right over here as the square root of -1 times the square root of x. And so really, the real fault in this logic, when people say, hey, -1 can't be equal to 1, the real fault is using this property when both a and b, where both of these are negative numbers. That will come up with something that is unambiguously false. If you expand your definition of the complex, or expand your definition of the principal root to include negative numbers in the domain, and to include imaginary numbers, then you can do this. You can say the square root of -x is the square root of -1 times or you say the principal square root of -x, I should be particular with my words, is the same thing as the principal square root of -1 times the principal square root of x when x is greater than or equal to 0. And I don't want to confuse you. If x is greater than or equal to 0, this negative x, then is clearly a negative, or I guess you say a non-positive number.
Alright, and that's all for today. Thank you guys all for watching. Tomorrow we're going to be doing what are complex numbers and the complex plane. So thank you guys all for watching, and